Right, how are we looking for all the stuff we set up here? That looks kind of okay. Get some micro. Whoopsie. Okay. Chalk and tea. That's what we do now. We do chalk and tea. How is this going? Wow, super confusing. Okay, that's cool. I think we're all set up for doing what now? I have no idea. I probably should be pushing forward with Nathan a little bit. Maybe that's what we'll do. Is this going to be one of those streams where I'll be like, yeah, let's do this thing, and then zero progress is made? Yeah. There's a possibility. I need to make a GitHub. I need to make a GitHub. All right, well, there you go. Are we signed in here? I need to add a repo. I am not. And all my keys are on the other side of the room, so we're not going to bother with that. Hello, Lee. How you going? We're going to do this. Whoops. We're going to do this. That's what we're going to do. Hello, Riz. How you doing? How's your words per minute now, Leet? How's that going? Hello, Yuzef. Hello, Cass. How are you going? Look at that. Look at all the beautiful bunnies in the chat now. Isn't that pretty? Pretty spectacular, isn't it? Right? It's improving a lot. Good work. Good work. I'm kind of going from bad to worse to good to bad to worse. I think I'm swapping between my laptop and this keyboard so frequently that I'm kind of okay. It's just the shift and control that trips me up, right? I have not. But you can share a screenshot, if you will. Learning Rust by doing Rustlings? Ah. Yeah, I showed Marek my take on Rustlings yesterday. He hadn't seen Rustlings before. So that makes sense. But yeah, maybe I'll do a YouTube short on that. I had a joke once. I cherished it, and now it's gone. Have I ever explained pinning? No, Riz, I have not. I give everyone the same. Everyone gets the same explanation, and everyone shares the same explanation, even though pinning is vastly. Maybe we should look at pinning today, right? But it's one of those really. It has a very simple explanation. What is pinning? Well, you pin something to its memory location, meaning while it's pinned, it's not allowed to move. Great. What a wonderful explanation. That seems very simple. How does it work? I don't know. Right. What I would say is to not go ham on your layout changes. Okay, you got both carriage returns there. I rarely use this thing, so this one is just my get my cabling source. So this is just an alternative to my layers. Wait, where are your layer switches? Where are your layer switches? What? 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 I don't even know what to believe anymore. No, that makes sense, Landlord. I do, but so you can think about layers as like just, and you got like you're using double escapes. What are we missing? No function keys. You have literally no function keys. That must trip you up. Function key. What else am I missing? Okay, maybe these are kind of sensible choices. Where's plus and minus? There. Okay, I understand. These are plus and minus, right? And underscore subsequently. Gotcha. Yeah, this is really good, Cass. Read this. Yeah, so I actually so now I have some context. If you were to read this, you would find these two here. These are worth looking at. All right, can't do that. The sources. I mean, you can skim through this. This is just about lifetime elision, right? But these two are useful to look at. Yeah. Ahoy, robotic. How you doing? Yeah, so I'm a little bit paralyzed as per usual. But we'll get there. Trying to figure out. So should we look at pinning? Weekend should be long. So this is where there's probably like a lot of questions around it. I wonder if we could internalize it. But the thing is, I never use pinning, right? I very rarely have a reason to pin anything in memory. And you can't use it without unsafe anyway, right? Who's asking about pinning? Was it you, Kath? No, it was Riz. So, it's simple, but the invariant is hard to follow. Exactly that, right? So, it's really pinning conceptually is very, very simple. You pin something to a location in memory, therefore it's not allowed to move. But what does that even mean? How do you prevent the moving? Can I pin anything to memory? How do I unpin something? There's a lot of questions, and there's a lot of MISC rules on what you can and can't do. And the fact is that you can violate these rules because a lot of it's going to be involved in cushing. That's not what I wanted to call this. Right, so if we were to have, I think a classic example is like a self-referential type where you have a string, and then here you would have a string slice, and this string slice is actually pointing to this string, right? So we already have problems talking about this. Hello, Byron. We already have problems talking about this in Rust because Rust does not update pointers. So if we, for whatever reason, could express this, the moment you move this thing, you might be moving this thing as well, right? I don't know what FOMO for layers means, but I have to have layers, right? I can't do without layers. There's so many things I have on layers, right? But it's all tickety-boo. I know what FOMO means, but I don't know. Oh, okay. Right. Sorry, I'm being a dimwit, but not because of that. It's because I didn't understand the context. All right. Thank you. Yes, you're absolutely right. So I read this as I have FOMO for layers, as in I have a car for sitting, I have a table for eating, I have FOMO for layers. Like you had FOMO for layers as layers, right? Okay, I'm a little bit simple. Don't hold it against me. All right. So if we could express this thing, right? Yeah, that has nothing to do with it, right? Because you're just pinning the location to the thing. The problem is once we pin something in memory, we can't move it, right? So the reason why we can't have this string reference point to this, well, let's try to create an instance of this thing, right? Okay, so the first thing we need is a string here, okay? Now our second problem is, what do we put here? We can't put anything here, right? We can't access this memory while we're initializing this thing, right? So we have to make the string first. Okay, now we can do this. And now this can be a reference to the string. Of course, we can't do this either, right? So let's pretend that this has memory address 0123. And this is now saying, okay, this is at 0123. And then here, move what is at 0123, right? So we've invalidated this memory address, right? Okay. We can lifetime promote to static and segfault. Yeah, we're not gonna do that. So this doesn't work, right? This will never compile, right? Also, what lifetime do we put here? We haven't even got to that part, right? We would need a lifetime of self, but that doesn't exist. All right. If we do this, then we're kind of implying that this thing comes from the outside. We could do this, of course, and get it to compile, but they're not pointing the same value anymore, right? I'm all right, Quick. How you doing? So this is why this is a problem, right? So the way we can get around this is say that this is now a const stir instead, right? Or it can be a const string if we want to, right? So we can have a pointer to a string instead. And now, once we've done this thing, what we start off here with here is actually a null pointer. Okay. Well, we don't need that anymore. Right? So we managed to get this to compile, but this is a null pointer. That is horrible. We can't have that, right? So if we made a new function here, and we take a string in here, and then we're going to do the same thing for this. But before we return this thing, we are now going to say that, all right, we can't call it self, right? What do we need here? We need this thing to be new. Like that. Okay, so now we have to make a change here. So we have to say that our instance.sref is equal to instance.s. Well, we have to make a pointer of this thing, right? As const. Okay, right? So can we have another function here? Sref takes a reference to self, returns a reference to a string size, and then we're gonna do an unsafe colon here, and we'll say self.sref deref. Okay, right? So let's add some value in here then, right? Oh, that's crazy. I have never seen this kind of explosion in the past. That is like the worst. That is the worst. That is the most beautiful error I've ever seen. I doubt we can get that again. If we could. That is so nice looking, right? Hello, Govinda. How you doing? Reference versus clone. And a clone would be to copy all the memory, right? So when we dereference this thing, we wouldn't get the same, right? All right, there you go. Because we transmuted this thing by accident. Well, we didn't. We interpreted a pointer as something else, right? We can get around this if we say const stir here instead, and we'll be fine, right? All right, you know what? Let's not. Let's just go with that for now. Whoops. No, back you go. There we go. Right. Okay. Oh yeah. I mean, probably right. Very much so, right? That's some good Rust. Yeah. So, but now we can get it right. Now we don't interpret as another type, right? And we're good. But here's a problem, right? We can do this. We can do this, right? We can print a hello world twice, but what if we were to do something like like that. Whoops. Okay. We moved something that we held a reference to. No, it didn't. Hang on. This is still breaking. Oh, this is kind of gorgeous, isn't it? Wait, why is that breaking? Is it because we're writing into that memory location? It is too. So we are we're not pinning this thing in memory though, right? We're not pinning this thing. This thing is free to move, but it has already moved here, apparently. So why don't we find out what is it that we're actually looking at here, right? And we can do that by saying inst.s. Can we do this? What was the raw keyword? And then we are not going to do any of this, but we're going to do this. Yeah, look at that. They are different memory addresses, right? The reason this was printing hello world was because there were still bytes in memory from before, right? Or maybe they're pointing to the same memory, but the location that we're pointing to. Okay, so hang on, I'm not making a lot of sense to you, right? This is a pointer to this field, not to the first byte in the string, right? So this is pointing to this field, and we are moving this field here. So actually, we're not moving the field here. We're assigning the field here. So we're assigning this address, and then when we're moving the instance, we are moving this field. Not what this field is internally pointing to, but the field itself. That's why the address is different, because we moved it. It's a little bit crazy, right? So what we have to do for this is pin this in memory, right? If we were to do something like that, we would have to pin it in memory, right? Yeah, we can have a look at this. I don't remember. Okay, it is sometimes useful to be able to rely upon a certain value not being able to move in the sense that its address in memory cannot change. This is useful, especially when there are one or more pointers pointing at that value. Thank you for the follow. The ability to rely on this guarantee that the value a pointer is pointing to at its the value is pointing at its pointee will not be moved out of its memory location, more generally remain valid at the same memory location. So this one, I don't actually know what the definition of valid is here. We haven't changed the bytes, we haven't changed the type, we haven't changed any provenance. I don't know, right? It's called pinning. We would say that a value which satisfies this guarantee has been pinned, in that it has been permanently, until the end of its lifespan, attached to its location in memory. Okay. As though pinned to a pinboard. Pinning a value is an incredibly useful building block for unsafe code to be able to reason about whether a raw pointer to the pinned value is still valid. As we'll see later, this is necessarily from the time the value is first pinned until the end of its lifespan. This concept of pinning is necessary to implement safe interfaces on top of things like self-referential types, which is what we have here, this being one of those self-referential types, right? An intrusive data structure we cannot currently be modeled in fully safe Rust using only the borrow checker references. So in essence, we can, once we have this, we can never do anything with this value, right? This value should never be allowed to mutate while we are assuming that this pointer is valid, right? So the value effectively has to be pinned here, or not this value, but this value has to be pinned. This S value is what has to be pinned. Pinning allows us to put a value which exists at some location in memory into a state where safe code cannot move the value to a different location in memory or otherwise invalidate it at its current location. So for this, it would make sense. We shouldn't be allowed to mutate the string. If we do, then we could change. Well, I guess that wouldn't actually be a problem. This, first of all, this can never work because this S is living on the stack. So we need the value to be moved to the heap, right? While the value itself is on the stack, it will end or move the moment we do this, right? The moment this function call is over. Hello, Temporis. How you doing, buddy? The moment this function call is over, it's like this. If you have a function, anything that you declare in this function is gonna be on the stack. And when the function is over, the frame, the call frame, the stack frame, sorry, is, well, it still probably is on the stack, but the stack pointer doesn't point to it anymore, right? It's, for all intents and purposes, that memory is no longer valid, right? Hello, Kenny. So that value is no longer valid. So anything that we allocate on the stack is either going to be gone or returned. And if we return the value, it has certainly moved, right? If we return this value isn't at the same memory location anymore, right? Which is the problem that we have here, right? So in essence, what we should have is a boxed string. And this thing is still pointing to a string, not to the box string, but is pointing to the string that the box has encapsulated, right? If we do this, then this value is on the heap, and when the stack frame ends, we can still have a valid pointer to that memory, right? Yeah, in Golang, you have a garbage collector anyway, so you would increment the count or whatever garbage. Maybe it's a tracing garbage. What do I know, right? But the long and short is you don't have to worry about it because something else is tracking this for you, right? And keeping you sane and grounded. I would assume Vulkan binding is like, okay, no idea what you're talking about. Wait, hang on. Sorry. Yes. Like Ash used pinning to avoid invalid pointers. There's a lot of structs that can probably, okay, I know what you're talking about, right? No, probably not, because this is a lot of C interop. There is no reason for you to pin memory when you are using foreign function interfaces. It has to, first of all, with FFI, it has to be clear who's the owner of the memory, right? You can't make those guarantees if some C code or C++ or whatever gives you a pointer to some memory, you have no guarantees that this memory will be freed by the library that gave it to you, that it will be valid at any given time. You don't know anything. You have no guarantees. So pinning it is probably not okay. That might be making a false guarantee. Hello, Doddy. It's Rust today. It's Rust today. Okay. So to pin means to attach something to its memory location. And it's harder to pin things to the stack than it is to the heap. Why will probably be made clear here. I'm just regurgitating something I remember, but not entirely the reasons for why. It allows us to put a value which exists in some location in memory into a state where safe code cannot move the value to a different location in memory, which is what we're doing here, right? We are moving the value. For this to be valid, we need to box S, right? But before we do that, we now need to get a pointer to S. This S, not this S. And we need to pin this, but we'll get to it. We'll get to it. Unless it implements unpin, which we'll talk about below. Anything that wants to interact with the pin value is in a way that has the potential to violate these guarantees must promise that it will not actually violate them, using the unsafe keyword to mark that such a promise is upheld. So this is where things gets a little bit sketchy, right? I can have a pointer and use an unsafe block to read that memory address, to visit the address and see what's there. And I can do the same thing with pin. There is nothing preventing you from doing something wrong. You're making a guarantee, but at the same time, you can't necessarily uphold that guarantee. Because, well, you can, but someone else using your library might not. This is where this is a little bit sketchy. So far, pinning feels very much like, I promise I won't. And that's also unsafe. All right, but I'm sure it makes sense. We can allow other unsafe code to rely on any pointer that points to the pinned value to be valid to dereference while it's pinned. As long as you don't use unsafe, it's impossible to create or misuse a pinned value in a way that is unsound. See documentation of pin pointer for more information on the practicalities of how to pin value and how to use that pin value from a user's perspective without using unsafe. The rest of this documentation is intended for to be the source of truth for users of pin pointer that are implementing the unsafe piece of the interface on pinning for validity. Users of pin pointer in safe code do not need to read this in detail. Okay, there's been an update to this documentation, right? So we can have a look. When we say a value is moved, we mean that the compiler copies byte for byte the value from one location to another. In a purely mechanical sense, this is identical to copying a value from one place in memory to another. Do not confuse this with cloning values in the heap. Yes, you're copying bytes from one place to another. Here, we're talking about a byte copy that is mem copy in C and is very fast compared to copying large chunks of bytes on the heap because large chunks of bytes are large, right? Yes, pinning should probably never be done with FFI because you cannot uphold any of those guarantees, right? In Rust, move carries with it the semantics of ownership transfer from one variable to another, which is the key difference between a copy and a move. For the purpose of this module's documentation, however, when we write move in italics, we mean specifically that the value has moved in the mechanical sense of being located in a new place in memory. All right, so, hopefully that makes sense. All values in Rust are trivially movable. I mean, it are, right? We're moving this value in here, right? This is understood by most, right? This means that the address at which a value is located at is not necessarily stable in between borrows, right? Again, we're pointing to the value, not to the string's first byte. The compiler allows to move a value to a new address without running any code to notify that that its address has changed, which is why we can't have pointers aren't self-updating, right? Although the compiler will not insert memory moves where no semantic move has occurred, there are many places where any value may be moved, for example, when doing assignment or passing a value into a function. So this is creating a mutable pointer to self as a usize. Which is weird because that's an option, but okay. All right. I now got caught up on. I got hung up on this more than anything. And so we're casting self to a usize. We're just looking at the address, so we're not really holding a pointer to a usize. I think that's just confusing, but I am making it confusing. Here we're reassigning the address, and here we're checking the pre. Okay, all right, this makes sense. This makes sense. So just to be clear, it's never safe to cast a pointer to a usize, even though they are of the same size. A pointer holds additional information that you can't just get rid of. Or you would get rid of it if you did this, right? Create a tracker and store the initial address. So this is, but every time we do a check for move, we're probably going to have like a move function which does a swap and sets the previous address, and that's why this would indicate something, right? May panic, yeah. So we're creating. So this may or may not move, right? Rust does not guarantee that check for move will never panic because the compiler is permitted to move tracker in many situations. Common smart pointer types such as box and mutable reference to T also allow moving the underlying value they point to, meaning you can take this out of memory, right? You can move out of a box, or you can use mem replace. We used mem swap in our previous example to move T out of a mut T. Therefore, putting a value such as the tracker above behind a pointer is enough for its own on its own to ensure the address does not change. So, well, this wouldn't. Would this change the address or just what it's pointing to, though, right? We say that a value has been pinned when it has been put into a state where it's guaranteed to remain located at the same place in memory from the time it is pinned until its drop is called. Address sensitive value, also known as when we need pinning. Most values in Rust are entirely okay being moved around at will. Types for which it is always the case that any value of that type can be moved at will should implement unpin, which we'll discuss below. Pin is specifically targeted at allowing the implementation of safe interfaces around types which have some state during which they become address sensitive. A value in such an address sensitive state is not okay with being moved around at will. Such a value must stay in unmoved and valid during the address sensitive portion of its lifespan, because some interface is relying on those invariants to be true in order for its implementation to be sound. As a motivating example of a type which may become address sensitive, consider a type which contains a pointer to another piece of its own data. This guy, right? In essence, a self-referential type. In order for such a type to be implemented soundly, the pointer which points into self data must be proven valid whenever it's accessed. But if that value is moved, the pointer will still point to the old address where the value was located and not the new location of self, thus becoming invalid. A key example of such a self-referential type are the state machines generated by the compiler to implement future for async functions. So pinning is very closely associated with async Rust. No, so only if you can make the guarantees, but I don't think that it makes sense to pin anything and then have it come from C or pass it to C. We don't even have to say C. Pass it to outside of your pass it all across FFI boundaries, right? Because you have no guarantees. Pinning it doesn't change anything, right? It doesn't change anything for the nature of the pointer, right? Does const not guarantee a pin? I don't think you can make a const value and say that it's pin. So const, I think it would make more sense to say that a static, an immutable static value could guarantee pin, maybe. As long as it doesn't... No, because you can have internal mutability. So const is just... const is just compile a copy and paste, right? So there's no difference there. A key example of such as several types state machines, yeah, right. Such types that have an address-sensitive state usually follow a life cycle that looks something like so. A value is created. A value is created, which can be freely moved around. Calling an async function, which returns a state machine, implementing future. An operation causes the value to depend on its own address, not changing, calling pull. All right. Further piece of safe interface of the type use internal and save operation, which assumes that... Okay, I'm missing something. No. Further pieces of the safe interface of the type use internal unsafe operation, which assume that the address of the value is stable. Subsequent calls to poll. Before the value is invalidated or, for example, deallocated, it is dropped, giving it a chance to notify anything with pointers to itself that those pointers will be invalidated, dropping the future. There are two possible ways to ensure the invariance required for 2 and 3 above, which apply to any address-sensitive type, not just self-referential types. Do not get broken. Have the value detect when it's moved and update all the pointers that point to itself. Guarantee that the address of the value does not change and that memory is not reused for anything else, which we observed with the string. During the time that the pointers to it are expected to be valid to dereference. So there are other situations where this could work. We could have something like a function that gets some input in the form of a reference to a string, right? For the duration of this function, there is a guarantee that this address will not change, right? So it is perfectly fine to do this, right? Right? This pointer is perfectly fine to do, right? Right, we weren't quite done there, right? Because this value cannot change, right? So if we want to, we can have an unsafe function in here where we simply dereference the pointer to get ourselves a string, right? This is perfectly fine to do. There's nothing wrong with this code because we know that this thing can't move. If we have a mutable reference, things change a little bit. We would change what we're pointing to, although admittedly, this will still just be a string. So even if we had a mutable reference that we pass in and we did something like take on S, the only thing that would change is this is now pointing to an empty string and nothing else. So this is still valid, right? What we couldn't do is we couldn't return a pointer to this, right? This would be dodgy. Well, I mean, it wouldn't, but using it would be. Right? Using this pointer might be. Since we discussed Rust can move values without notifying them that they're moved, the first option is ruled out. In order to implement the second option, we must in some way enforce this key invariant, prevent the value from being moved or otherwise invalidated. You may notice this sounds an awful lot like the definition of pinning a value. There are a few ways one might be able to enforce this invariant in Rust. Offer a wholly unsafe API to interact with the object, thus requiring every caller to uphold the invariant themselves. Store the value that must not be moved behind a carefully managed pointer internal to the object. Leverage the type system to encode and enforce this invariant by presenting a restricted API surface to interact with any object that requires these invariants. And honestly, 3 kind of makes a lot of sense, right? We could have an API on self-ref where we would do something like oh, nice. Right. So this would never hold, right? Because there's no guarantee that we have gone through and set pointer, right? And then we say that self.sref is equal to, let's do away with the box here, right? Okay, so for this to be okay to do, we would have to call these 2 functions before each other, right? So like that. Now this is okay to do. I think maybe even Miri will be okay with this. We'll see. Why is self pinned? That's because you are not allowed to move it, right? So Miri is okay with this thing, right? It's to put emphasis that you're not allowed to move the value. You can have, so okay, look at this. Value is a pin of a mutable reference to a string in this case, right? I think this is roughly what it looks like, but instead of string here, you have self for a future, right? I can't do anything on this value without unpinning it. So even if I do this, actually this, is it because string is unpinned? It might be because string is unpinned then. Can we dereference? Can we dereference this thing where it's unpinned? That's just a quality. Here, I think this is it, right? So we can do this because this is doesn't care about being moved. We can safely create a facade pin which will allow the value to participate in pin bound. But if we did this, struct not pin, if we do this, not pinned returns something that impl unpin, which we have to bring in. Really? All right, no, it's already in there. Can we do this? So if we did this and we say T here, now this would probably not work. Although now the only thing we know about this is that it's not unpinned, right? So calling pinned with not this is fine, right? Is it because we don't know the type? All right, let's have a quick look at unpin for this thing. So what implements unpin? Any reference to T? Oh no, we want not unpin. So can we have this? We can. So if we do this, and it has a marker phantom pinned like this, then this thing would not be pinned, right? So this should work. Like that. So really, that's what we're looking for. But we can just use meh here instead then, right? And then we can get rid of this thing. All right. Keep forgetting we need that, right? What? Okay, so can we pin this thing now? No, we cannot. That's why if we took this out, this would be fine. But because we have this, this is not fine. So we're saying that whatever this is, it cannot be pinned. Hello, Privan. Yeah, we don't have negative trait bounds. We can't express it like that. That's why we need things like this, right? So this is why you can't make a struct that is not send, that just holds a string, all right? If we try to use this thing, it's still gonna be right? We can still call not send. We can still pass not send in here, right? So use send works with S, okay? Even if we don't want this, if we try to say not send here, this thing will freak out, right? Well, obviously, mainly because I just made that up. But if we said import not send for not send, there we go, right? This doesn't work, right? We can't do that. And then we quit because that's how we roll when I really want to just format my code, right? So this doesn't work, but there are ways around this if you wanted to. Actually, we don't need that. If you want to make something not send, you just have to put a phantom data in there. To something that points to something that is not send, right? Like that. Now this is fine. We've managed to implement not send for this thing. Oh, we can't do that either. But yes. We couldn't have negative numbers. Well, that's because you're supposed to be a positive individual. That's why. All right. The trait is automatically implemented for almost every type. The compiler is free to take the conservative stance on marking types as unpin, as long as all the types that compose these fields are also unpin, which is very much the same thing for send and sync, right? As long as you use types that are send and sync in your struct, then that's super cool, man. Nice. So what was I talking about, right? Oh, I'm almost done with my video, by the way. I finished. I have to do the ending, but the majority of the video is done. It's taking me, I don't know how many days, but the video is like 3 minutes long. Do you know how disheartening that is? You have 3 minutes of video. I spent 2 hours making one animation that was 3 seconds long as well. So an interesting tip about variables that might not have a positive integer type at declaration, which is set to the value -1 until the value can be changed when it's known. I don't understand this, Leet. At declaration, which is to set the value to -1. But if you can set it to -1, it's not a positive integer type. Then it is a signed type. So you already know that it's not necessarily positive, right? Maybe I misunderstand. I probably misunderstand. The trait is automatically implemented for almost every type, blah, blah, blah. This is because of if a type implements unpin, then it's if a type implements unpin, then it's unsound for that type's implementation to rely on pinning related guarantees for soundness, even when viewed through a pinning pointer. It is the responsibility of the implementer of a type that relies upon pinning for soundness. Okay, right. Oh no, we're reading about unpin. Oh man, back to this thing, right? But okay, sorry, I'm not like super into this, but just to put emphasis on it. So when we talk about pinning in Rust, and everyone gets the same answer, what does pinning mean? Well, it means that the value is pinned in memory and is not allowed to move. Okay, if it was that simple, then we wouldn't need this book here describing pinning and how all this stuff works, right? It wouldn't be this much around it, right? So the long and short of it is, I can't explain pinning, right? And maybe one day, I don't feel like doing it now, not explaining it, but learning it enough to explain it, right? It also feels like one of those things, if you made a video about pinning, people would watch that and then would just come away with still not understanding pinning. I just feel like that's the case. If I ever need to deal with pinning, that would probably be good, because then I'm going to have a chance to actually try to discombobulate the whole thing and figure it out. But for now, I don't have to, and I'm quite happy about that, right? I think maybe we should look at the... Do you feel like you have to use it to understand it? I think understanding pinning is probably just a couple of steps up on the rungs of understanding pointers and the invariance you have to uphold, right? So the reason this is complicated is because you can do whatever you want with unsafe Rust, right? You can cast a pointer to a sandwich and then treat it as a couple of chips and a gherkin, right? You can do whatever you want in an unsafe block. So the invariants you have to uphold, you can miss them, right? In the same way that you might accidentally type in an incorrect email address in a field or whatever, right? As in, it's a human error to uphold one of these invariants, right? And instead you end up with busted code and you don't know about it, right? I think so. First of all, self-referential types are incredibly hard to express in Rust. There has been multiple crates that try to make this a thing, but most of them have unsoundness issues, one somewhere or another. Some of them are sound as long as you use them in a certain way, but then again, that brings us back to the original issue, right? You have to do things in a certain way, and the compiler isn't necessarily going to tell you when you do it wrong. Something that we depend on in Rust quite a lot, right? So it makes it more complicated. This is why unsafe Rust is more difficult. I talked about this 1,000 times. I'm bored of my own voice, but unsafe Rust is harder than C, right? I say, as someone who's really good at C. Right. And here's where things gets a little bit hairy, right? Because you have to have these unsafe block. This should mean that the point EA can never move again. But you see, you can, right? And this isn't some kind of magical thing that happens. I think if we look at, oh, I'm not even in there. So we have so much mem swap throughout Anathema. Let's just count the number of lines of mem swap that we have, right? Ish, right? 39 lines using mem swap. Well, it's also going to show this. So, you know, you can probably think of that as maybe 30, but still, right? Yes, that is absolutely true. Or rather, unsafe is necessary when the Rust compiler cannot make the guarantees for you. And that is the moment you cross an FFI boundary, right? Then you need unsafe Rust because you don't know what the other library is doing, right? But that's in the same sense. It's like saying, you know what? No, that metaphor was so dumb it died on the floor. Let's do something. Let's do something a little bit less boring than talk about unsafe. Let's talk about safe instead. Safety. Yeah, no, it's anathema. I like how Marek says it. I'm never gonna correct him. He says anathema. He adds anan instead of ana. Anathema. Oh, well, no, hang on. Sorry, Kabeja. I understand what you're saying. You could pronounce it as anathema as well. I guess that's what you're saying. Not anathema versus... It's anathema versus anathema. And you can pronounce it however you want, right? However you want. As a matter of fact, we could find the correct pronunciation, but I'm not going to. I'm going to keep calling it anathema, just because. Whether that's right or not. Okay, now. Do we try to fix something just so we can release this? Yeah, you have anathema on your elbows for being out in the cold. My hand smells of aniseed. Like we have this like health food for the bunny that's packed with vitamins and stuff. And there's like star anise in there. It smells a lot, right? Well, this one actually has an answer, right? This one is described on, if you look at Linux Mint's website, it's pronounced like the T, mate, not as your English friend, your mate. But this one makes sense because mate is mate, right? It just happens to be spelled the same way. Mate, on the other hand, well, I'll let you know if we find any. Okay, so should we have a look at which branch we're on, right? Right, so state naming. What do we have here? We have like a lot of... Oh yeah, we started the second one. I don't think we're going to do that. I think we're going to get rid of the second one. But we do want this. So let's just get rid of widgets 2 from there. Yeah, I use Linux Mint for from 17 to 19 maybe on some of my computers. And I think Linux Mint is probably the best minty fresh thing you can use when it comes to getting into Linux. If you're new to Linux, Linux Mint is probably the sanest choice. I don't think Ubuntu is sane because you're leaving something disgusting and joining something some kind of somewhat gross sometimes, right? Yeah, I remember your asshole Amazon affiliate link baked into the doc, you piece of right? Anyway, let's not talk about that now. And that's mild, right? Anyway, so we added something new to the runtime here that I ain't gonna have a look at now. We're gonna get on with this. Okay, that's what we're gonna do. Cinnamon is really good. I use cinnamon, not mate. Virginity came back. Okay. Anyway, what is this rebuild? Oh yeah, that's the thing. Oh man, don't love that, right? Okay. We're missing something here. That's clearly not gonna be there anymore. There is a field missing here. It's true, yeah. It's true. Yeah, I never did much with cinnamon. The thing that I always liked about cinnamon or mint cinnamon was that it was such a it just works kind of distro, and it even had things built into the file manager for formatting and flashing images onto USB drives and stuff, right? GTK for his data. I mean, look what I'm using. This thing is older than half my chat. So I don't know. I don't know if I should be waving that stick around. Path list control. There you are. Okay, so you do exist. So what can we do with this thing? We can... Oh yeah, now I remember. All right, so we just have to start filling this up with changes, right? So really, what is missing here is having values in here and tracking whether something needs layout or not. So we have to make a decision. Why did I start this now? I am clearly in the worst frame of mind for dealing with this thing, but okay. Let's go and put the kettle on. Actually, we're gonna grab some vitamins and put the kettle on. I might actually skip the kettle. Let me just go and get a bottle of water. Okay. So, what are we at, right? We need to determine whether something needs to be repainted or not, right? That was the whole story, wasn't it? So that's what we need to fix here. And for that, I think we said we have this tree traversal thing. That's what we need. That now it's coming back to me, along with anxiety and performance anxiety and streaming anxiety. Not really. I'm kidding. Yes, it's the tree traversal. So I think maybe we had the cache. We ask it if it does a layout. Do we need to rebuild everything else? And that was the question, right? I don't think that's true at all. I think you are confused. You are not seeing right. These are not the comments you're looking for. Yeah, what else is there? Really? Yes, I'm happy to hear that, Scott. Morning to you. Yesterday was quite fun. For those of you who didn't watch the stream yesterday, I did a collab with another streamer, and we built nothing. We were sorry, I completely just stupidized my head again. I'm trying to find the YouTube thing. Oh, forget about it. Anyway, yes, we did a random language choice, and we did a task, and I had 1 hour to build a web server that served to-dos that you could get a single one, all of them, and toggle them as done or not done. And we did this in the Crystal programming language, a language I'd never seen before. Marek, who was the other guy, he was only allowed to use AI tools to do it, and I was allowed to use anything but AI tools to do it. And it was kind of fun. It was kind of fun to do. I think it's one of those things I want to do again, right? AI did good, yes. Yeah. He had a lot more than I had. I think he finished with 15 minutes to spare. I finished with 6 minutes to spare. His one seemed like properly set up and everything. But the more important thing is that I learned something about the language from speed running the documentation. But honestly, not really. I think we are both equally terrible at using Crystal. It was just a fun exercise, nothing else, right? Yeah, I like this path list because this one doesn't allocate, right? I don't think it does. Well, yes, it does. Okay, but we keep reusing it. Okay, it's over. As for Crystal, isn't it much faster than Ruby? I never benchmarked or looked at it. I never looked at Crystal until yesterday, and I just looked at documentation, right? I don't know anything about it. Okay, so maybe this is what we build. Let's build another tree traversal tool, right? So we have the tree walker, which I don't think is ever used. No, this is compiling. So the walker is never used. Then we can rewrite the walker to fit our needs instead. So here we panic. That's what we're gonna do. It's not implemented yet. And what is the behavior of the walker? It has to be able to move to a location in the tree and then do something else from there. Maybe I'm overthinking this. Maybe we just need to start caching values and observe the cache. And if there is no difference, how do we force a rebuild? Ah, that is the question. How do we force a rebuild? There might be might be some actual correlation there, right? Pokemon Pearl. I choose you, C-Pan. No, worst life choice. All right. So if we end up in a forced rebuild, so we kind of get into it saying use the cache. So we need to be able to cache it. That's the first thing to do. We need a better name than that. Yes, we do. All right, and there's a need for some debugging over there. Okay, so for this one, we could simply add a const 0. That's going to be self. New size 0. Constraints 0. I don't know if constraint 0 exists. Apparently it did. Then we don't store the size on self like that. We store on the cache instead. Ship. That might not be valid to do. Okay, this could... No. This is where I made a mistake last time I looked at this. So we're going to create the size here. And this is where we know if the size has changed. So now our layout here is going to return a layout instead. So we're going to get the size. And now we have to look at our own cache, right? If size is not equal to self.cache.size, then we're gonna do something. We need the constraints as well. There we go. Oh, the constraints might be different as well. Okay, in that case, we'll go to cache. We implement partial equality. And then we do that instead, right? So we create a new cache. Like that. All right, so this floaty business might become an issue, but I think we're gonna be okay with that. So if this is it, if this is the same, but we're doing the layout computation anyway. Now I feel like a stupid head. I don't want to be a stupid head. Being a stupid head is bad for making things work, right? I'm getting used to that gross flavor. Okay. We don't know if we should lay out or not. This feels so strange, right? Like, we don't know if we're supposed to do the layout or not, right? We could attach this information to the context, but that doesn't seem right to do. Let's stop drinking this for now. Okay. Hello, Kyoto Cheese. How you doing? So we traverse the tree until we find the thing that we're gonna change. Then we change it, and if it so maybe that is correct. Then here we're just gonna return layout same. I don't know what we're gonna do with floaty boys for now, right? So let's add a to do floating widgets needs to be dealt with. And then here we return a layout changed with self.cache.size. right? Okay. And this is an element layout that returns size, but it should return a layout instead. I don't think we're going to be allowed to access that, no. So we'll make this thing pub super only. We'll make this one pub crate. This is an element, so we could just call the size function here. Holy! Look at all those beautiful errors. Okay, shit. So, yeah, these are all the widget implementations, right? Okay, instead of doing that, then I don't want to return a layout anymore. I do want to return a size. But I want to determine whether I'm laying out the correct... Right. We're getting rid of this thing. Layout, you can push right off. We're done with you. We're done with you. So this is just going to return the size. Okay. Hello, Alan. How you going? So really, we're looking for different kinds of layouts, right? We're looking to know whether we are forcing a layout, whether we are just getting the cache value, or whether we are testing for a change, right? So if this was right, there's no reason to continue doing the layout if nothing has changed here, right? So anything else, we should in essence check the context. If context dot needs layout, then return self cache size, right? Epiphanies in Rust, how you can store structs in enums. Oh, yeah. Tell me more, Alan. Tell me more. And let's see if we can explore that a little bit. Because it's always nice. So now this becomes a question on the context. And if this thing isn't true, then we just go through the whole thing, right? So let's have a function here called needs layout that returns a bool, right? So if we have a function here called force layout, that's not a function, by the way. But can you have an enum that has a const? You cannot. I have different types of sections in my website builder. I'm using an enum to identify the types that then store structs that have the needed features for each section type. I have different type. I'm using an enum to identify the types. And then you have, okay, so you have, yes, you have struct variants, right? But an import block isn't, listen here, Tanaka, let me school you a little bit in Rust because I see that you're new. An import block is for a type, not specific for an enum. You can have an import block on an enum, you can have an import block, you can even have an import block on a trait. Okay, son, are you listening, son? Are you learning now? Kidding, buddy. For those of you who don't know what my stupid joke there was, right, you can actually do this. And now you can import all right. This is kind of perverse, but we're implementing this for the trait object. We're not implementing this for everything that implements lol. We're implementing this for lol, okay? Which is, you know, anyway. All right. Okay. Yeah, Alan. I guess I don't really have anything to add to that. I was hoping your revelation would be more perverse, but it wasn't. It was a straight up normal. Are you gonna pursue? So I guess there's not really much to add to it, right? Struct variants are really useful. Having a constant or specific variant, I don't know. You would like at best you would get some memory optimizations if you could do that, but you could. No, you couldn't. Could you? No, I think at best you would save a bit of memory, maybe, but you know. Okay, so we have the force layout here, which dictates whether we should or shouldn't do something. But we could also look at the node path to distinguish where to start. Oh, but that doesn't help either. Oh. No, it doesn't. So we end up, we still have to be able to go into the tree and then walk backwards again out of the tree with our change. That still holds. I think since I'm solving the same problem over and over again with the same solution, I think that is the solution to go with then. So we just need a mechanic to go into the tree. But we also need the force layout. So we need a mechanic to go into the tree, make a change, and then back out again. So it's kind of like we can visit nodes. Oh, how does this look? So we're gonna go back to the tree walker then. All right, well, no harm, no foul there. We just took a while to get back here. So how does the bot work now, Tanaka? Can I do marker sandwich? Whoops. Whoops. No markers yet. You said you had to add some commands. I don't know if you've done it or not. Anyway, if we do this, then we have to be able to set the path of the node walker. So maybe that has to be a particular struct then. Like that. So the walker is giving a path on where to go. Then, given a circumstance, this can change. And this thing should panic. Wow, how come it didn't panic? Oh, because we call this function. Oh, it's all good, mate. It's all good. Yeah, ping away. I'm gonna be at Sunday dinner, so I'll check my phone. So this creates a tree with the following layout. Then we apply the node walker to node with an ID of 2. This should change all the nodes on the way to 2 and all the children of 2. So this one, I mean, this is kind of what we want, right? This is doing what I did. How long ago since I wrote this? Over a month ago, I wrote this. Okay, but this is not done. There are things that we have to do here. So let's just think about this. If this was a widget tree and the target is 2, where is the target specified? This is the key. No, it isn't. Walker takes the parent. The walker takes the parent. What's the parent here? We apply the node walker to the node with an ID of 2. This should change all the nodes in the way to 2 and all the children of 2. Okay, that's the force layout being done. So if this is not the target, we need to know what happens when it's not the target as well. I guess we just call it a parent, and that's that. Yeah, so that just happens to be the target. That makes more sense then. $11. Okay, I have to go and feed the animals soon again. Sorry, I don't get a lot of streaming time when this is happening, but come Thursday, if you guys didn't know it, it's gonna be a terrible time for me. My kid's gonna dress me up like a My Little Pony on Thursday. So if you want to see that, you should tune in. Let me see if the stuff that she wanted has been... It's not arrived yet. Hopefully it'll turn up soon, though. Okay, what did I do now? Bollocks. Sorry. Okay, it arrived. Just gotta go and pick it up. Yes, she's gonna paint my face pink and my hair. So on Thursday, I'm gonna have to spend the first day as a normal person. We know that's not true. But yes, the first part, we're gonna do a stream, and then we're gonna end that stream, and then we're gonna do another stream where this is happening. We're gonna do it. I'm pointing at something you guys can't see, but I have a table next to me with a different camera set up. It's gonna be joyous and terrible. Okay, anyway, so we have this now. Around what time? Let me see, what time are you in? We can do this. And I will tell you. It will be... No, that's not the right... Probably around 8:30 CDT. Okay, let's do UTC then for anyone who wants to do that. So it will be around... Oh, well, that was easy. Around 2 p.m. UTC. I will announce this on Discord as well. I will keep reminding people about my horrible humiliation. Okay, does the walker know the distinction between apparent or not? It does not. So this is going to apply. So this should be applied to parent, but it's just going to do an apply. So there's no distinction there. So we do end up calling layout on the node, right? It's just a question of whether that node is changing or not. And we have no return value here either. nor do we have a filter. So we're just calling apply, and there's no context to propagate. So of course this doesn't work. Do we have access to this on the... let's have a look at the tree module for the filter. Where's the full... Why? Do we have... What is this value? Is this the path? That is the path. We could just pass the path in here as well. That could work. So if we end up with a value, we're doing this. But we have to add a path filter to that for it to work. So we have to modify the filter we have for this, for the layout. So let's have a look at the layout filter then. Here's the layout filter. We don't get access to the path here. Do we have attributes, but we don't have anything else on there. We probably need other things on there. Oh, the complexity of this thing. If we store the path on here, then we can tell when we reached a certain node. But what does that tell us? This is just determining whether this thing is included or not. So maybe this is not even the right thing. No, it comes back to the same cursed thing, right? What we refer to as the children on the default widgets. Let's look at the many. These are layout children, which is just a tree for it. But we could store additional information on there, couldn't we? Oh man, this is complicated, isn't it? Right. So here, when we call the... Oh, my back. When we call the layout here, we have a context. Where does this context come from? It comes from here. So here, this should dictate whether we need to do the layout or not, right? So if we could determine... and how do we do that without having to change this? So the thing that we do here is just returning the cached size. So this becomes really fast, right? Although there's still a cost if we do this over multiple widgets. There's still a cost, even if we had like 65,000 widgets. What did we do in terms of benchmarking that one time? We had some kind of Threadreaper. Oh yeah, no, that was the library for killing threads that didn't make sense. What's Resi? Is that one of you guys? No, that was the result thing. I need to make a video on that one as well. No. None of this contains the benchmark code. So did we just... No, it was World. World has it. And how many... Static something. How many do we have? 5,000 to 10,000. Just iterating. Okay, so all right. So that kind of means something, even though it doesn't. We don't want to call it with the same... We don't want to call it multiple times, though. Maybe we could just add that into the context. But then how does the node find out where it needs to lay out or not? Because it has no awareness of self. We could store an ID instead. But then we have dirty widgets again. So when we go to do a layout here, we have the ID. So if the context doesn't force layout, and that is not in the list of dirty widgets, currently this is path control. If the context doesn't force layout and the ID is not in the list of dirty widgets, then... Hello, Bipop, how you doing? Then just return the cached value, right? So for the first round, we'll say force layout. For the second round, we're dealing with updates. Okay. Now, if we return the cached value, that still means that we have to go through every node and ask it for the cached value. Which I guess isn't too bad. That would arguably be quite all right. So if we end up with a change, then we need to mutate the context. So when we hear, if this has changed, then we need to say context.force layout is now true. Right? So if this is not, then we do that. Then we're forcing layout going forward. And this check can be had before. This check can be done here. we need to pass in self ID. I don't think that returns a widget ID. So what we call the control list, the path control, has to become dirty widgets again that contains a collection of widget IDs that has changed. So even though the path list was really fun to write or the prefix list was really nice to write and I thoroughly enjoyed it, it is now the wrong tool for the job. Why is this thing not working? Oh, right. We should be able to just call size here, right? I think this is correct, but again, the complexity is spread out. The functionality isn't. We need more types and more clear lines in the sand, metaphorically. We don't need sand in here. But I think this is it. So this thing, I think that's all we need for the layout. So if you have 30,000 widgets, you're still going to have to go through 30,000 widgets, but you're just going to grab the cache. You're not reflowing the layout. So if you have a widget with 30,000 widgets in it, but this widget isn't marked as a dirty widget, you're just grabbing the cache size, so you don't have to reflow that. I think this is right. We just have to get dirty widgets back. It's sad to ditch the prefix list because I really liked it, but it's not the right thing to use here. All right, what we're going to do is going to commit this now. Yeah, we deleted that. Okay, so we're caching now. I think that's it. I don't know what we're going to do for position. I do want that one. Cache the size and constraint. Okay. So yeah, short stream, but again, I'm streaming every day as promised. I'm gonna go and feed my sick little fur baby. I will be back tomorrow tomorrow we'll do a longer stream, but it will be interrupted every 3 hours for feeding and such. Thank you guys for hanging out. Have a wonderful Sunday, and I'll see you guys.